if I were to put a substitution problem on the exam, it would likely be a substitution problem where you can tell exactly what the substitution should be without having to think too much, or it'll be what's called a Bernoulli substitution. And a Bernoulli substitution is a differential equation of the form y prime plus p of xy equals q of x y to the n. This is a particular type of differential equation that it turns out that we can solve for all values of n. And I want to just point out a few things right away. First of all, if let's call this differential equation star, but if n is equal to 0, star is just going to be first order linear. Okay, and that's where you have y prime plus p of xy equals q of x. So it's right there in that form. And if n is equal to 1, then what you could do is you would have p of xy equals q of xy with the y prime, and so you'd have you could get the linear terms together, is what I mean, and then it turns out that star is separable. Okay, and so we don't really need to worry about the cases when n is 0 or when n is 1. And so it turns out that what we're going to do to get this in the right form is we're going to divide both sides of this equation star, by y to the n. So we're going to have y to the negative n, y prime, plus p of x, y to the 1 minus n, equals q of x. So just dividing both sides by y to the n. And then it turns out what our substitution is going to be is it's going to be that middle y term. So what we're going to substitute is u is y to the 1 minus n. The reason for that is that du is going to be, well, what this now we don't really have to think of this as a function of multiple variables. This is just really a u and a y. There's no x's. So we don't need to worry about differentiating by x because that part is 0 is what I mean to say. So what this is going to be is we're going to end up with du dx is going to be 1 minus n y to the minus n dy dx. And notice that we have y to the minus n dy dx, y to the minus n dy dx. We just have to deal with this 1 minus n. And so what we can do is we can divide both sides by that 1 minus n. We know that n's not going to be equal to 1, because if it is 1, this is a silly thing to do. So we can assume that n is going to be different than 1. And then this whole thing kind of falls into place. This is the right substitution. And then this becomes something that you can solve. Okay, and so let's go ahead and let's do a few examples here. Okay, so again, these are called Bernoulli substitutions. So let's solve y prime or dy dx. I don't really care how you want to write it, but dy dx is equal to 2y over x plus 3y to the 4th over x squared. Okay, and let's actually make it an initial value problem. Let's say that y of 1 is equal to 1/2. And so this is going to be our differential equation that we'll solve. We can do a few things if you like. We can, if you want to do this, we can move it doesn't really matter at this point, but we could move this piece over if you want it to look more like the problem that we had above, the generic form. So if you want to do that, that's fine. At the same time, we should divide by this y to the 4th power. Our n is 4 here. And so what we're going to get is we're going to end up with y to the negative 4th dy dx minus, so this is going to be minus y to the negative 3rd times 2 over x equals 3 over x squared. So we did two things there. We moved this 2y over x to the left side, and then we divided by our y to the 4th term. And now we're ready to substitute, and we're going to end up with this y to the negative 3 is our u. Let me make just a little bit of room here. So we're going to substitute u is y to the negative 3 du dx is going to be negative 3 y to the negative 4 dy dx. And we have y to the negative 4 dy dx, so we'll move the negative 3 over. So negative 1/3 du dx is equal to y to the negative 4th dy dx. And now we're ready to substitute. So our y to the negative 4 dy dx is negative 1/3 du dx minus y to the negative 3 was u, so minus 2 over x times u. And the right side is just what it is, 3 over x squared. And notice that this is now a linear equation in u. So now we can use what we know, and we can solve this as a linear equation in u. So let's multiply both sides by negative 3 so that we can have our du dx with a constant 1 in front. So we have a du dx plus 6 over x times u equals negative 9 over x squared. And then remember, the trick with linear differential equations is to find the integrating factor. In our case, our integrating factor is going to be e to the integral of 6 over x. So that's going to be e to the 6th natural log of x, which will be x to the 6th. And so if we multiply both sides by x to the 6th power, we're going to end up with x to the 6th du dx plus 6x to the 5th times u equals negative 9x to the 4th. And the left side we can recognize as the derivative of the product x to the 6th times u. And so if we integrate both sides, we can drop the derivative on the left. If we integrate the right side, we'll end up with negative 9/5 x to the 5th plus c. And now we're ready to divide both sides by x to the 6th. So we'll end up with u is negative 9/5 times 1 over x plus c over x to the 6th. And then finally, we're going to substitute back. Remember that our substitution was u was y to the negative 3. And so if this is our expression for u, that means that this is y to the negative 3. So this is negative 9 over 5x plus c over x to the 6th. And then we can take, you can do this however you like. You can combine the fractions, flip them, take a cube root. Or if you want, you can just say that y is going to be whatever this quantity is. So negative 9 over 5x plus c over x to the 6th to the negative 1/3. And just leave it at that, and I'm totally fine with that. Okay, and again, you can simplify that a little bit more if you like, but that's totally fine. Okay, so that's an example of a Bernoulli substitution.